So hi everyone, welcome and thank you for joining us for today's webinar. First, let's do some housekeeping announcements. Today's webinar, like all webinars, is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and the presenter will have their microphones enabled, so please use the chat window to type in your questions or to communicate with others. During the question and answer session at the end of the talk, if you would like your mic enabled, please raise your hand. Today's webinar speaker is Gharti. He received his PhD in geophysics from the University of Oslo and Norway, and a Master of Science in Earthquake Engineering from the University of Tokyo in Japan. Gharti is currently a postdoctoral research associate at Princeton University, where his primary research interests include computational geomechanics, including glacial rebound, wave propagation, inverse problems, and microseismicity. These interests have led him to contribute to the SpecFEM family of codes, and in particular, he will discuss in his talk the implementation of the spectral infinite element method in SpecFEM to solve problems requiring full gravity. And without further ado,
okay, so hello everyone, good afternoon. I am Nath from Princeton University, and today I'll introduce you to the spectral infinite element method, and which we believe is able to solve many interesting problems in global geodynamics. So this is the outline of my talk. First of all, I will briefly describe the background behind our work, and then I will briefly describe the infinite element method and how it can be combined with the spectral element method to solve full gravity problems in global geodynamics. And finally, I will demonstrate some examples. So there are several interesting problems in global geodynamics. For example, earthquake wave propagation, post-earthquake relaxation, glacial isostatic adjustment, tidal loading, and a lot of things. So this is pretty ambitious wish list to try to solve this problem. But fortunately, these all problems can be represented by a single set of governing equations. The first is the conservation of linear momentum, where sigma is the stress field, u dot and u double dots are respectively the particle displacement, velocity, and acceleration. And rho is the mass density, g is the background gravity, and phi is the gravitational potential, and omega is the rotation rate, and F is the volumetric force. And this is the linear equation, linear representation of the conservation of linear momentum. And the second equation is the conservation of angular momentum, and which has the nonlinear dependence on the displacement field. And finally, the third equation is Poisson's Laplace equation, which represents the gravitational potential in all of space. So we want to solve these equations, but first let's explore what the existing package like SpecFEM 3D Cartesian or SpecFEM 3D Globe can achieve with these equations. The first, the SpecFEM 3D Cartesian solved just two terms in the conservation of linear momentum, and it is remarkable to see that just considering these two terms, SpecFEM 3D Cartesian is able to solve several problems in geophysics. And similarly, the SpecFEM 3D Globe includes more terms particularly related to the background gravity and rotation rate in the Earth. And we can also include the volumetric force such as black hole or potential due to the Earth or Moon in this SpecFEM 3D Globe. And basically now also it solves only the conservation of linear momentum, and it discards the perturbed gravitational potential. So this is, that's why it's so-called the Collin approximation. But now we want to look into the other problems like glacial rebound or the normal mode long period seismology. Then we cannot discard this gravitational potential, and we must solve the Poisson's equation. That's why our motivation or main goal is to uncover this gray area from this page literally, or we want to solve the complete set of governing equations for the earthquake geodynamics. So yes, we want to solve this problem, but there are some big challenges. And first challenge is the problem size. So just to show you some tentative idea, so I consider simple Earth model. So in order to mesh this model, we need to decompose this into 6 chunks, like rectangular chunks, and I consider the NEX equal to 256, which is just the number of elements on each direction on this chunk. And with this NEX equal to 256, the number of spectral elements is about 4.5 million, which results in the number of nodes that exceeds nearly 300 million, which is a big problem. So now, the SpecFM3D Cartesian or SpecFM3D globe solves only the explicit time scale problem. So that means we basically invert the mass matrix, and this vector matrix multiplication such as Ks and Cs dot can be achieved in the element by element fashion, and the mass matrix in the spectral element method is always diagonal, and that's why the maximum array size that we will be dealing is just the number of degrees of freedom, and which is more than 1 billion. But to solve this equation in a complete sense, we also have to solve this equation in the implicit framework, and then we must invert the stiffness matrix, and which is generally not diagonal. That means the maximum array size that we will be dealing is insanely huge, which is about more than 1 billion by 1 billion, and you can imagine that this problem simply cannot be solved. So how can we solve this problem? Or how can we mitigate this huge problem? Well, fortunately, the stiffness mass matrix is sparse. So in the figure, what you can see is the picture of the stiffness matrix, the typical stiffness matrix in the globe. So the bright color is the non-zero elements of the stiffness matrix, whereas the dark blue color is the zero elements of the matrix. So we can actually squeeze this matrix and take advantage of the sparsity, or sometimes we can solve this kind of equation in element by element fashion, which saves some memory, which is more efficient than the original one, but still it's a huge problem. And fortunately, we have access to some of the most powerful computers, and that's why somehow we managed to solve this problem. So another serious problem in this kind of problem is the gravity. So in figure, you see that the IC is the inner core, which is solid, and OC is the outer core, which is fluid, and CM is the first mantle, and OS is the outer space. So first, we need to define the boundary condition carefully on this model. The first, on the solid fluid boundary, we need to satisfy the continuity of the traction and continuity of the normal component of the displacement. So this is not the big problem. And similarly, on the free surface, we need to define the traction. So if it is traction free, then just the traction will be 0, like for the earthquake wave propagation. But if we are dealing with, let's say, glacial rebound, then we need to consider the ice load for this traction. And finally, we know that gravity decays to 0 at infinity. So that means the boundary condition for gravity is defined at the infinity, and which makes this problem unbounded domain problem or the infinite domain problem, and which is the big challenge to solve this kind of equation numerically. Well, there are some interesting methods to tackle this problem. The first option is to extend the domain as big as possible and consider that P, or the gravity, is 0 at that outer surface. And as you can imagine, that we need very big model to approximate in this manner. So the practice shows that we need at least 10 times bigger the original model to approximately or reasonably approximate the gravity field. And that's why it is not efficient. And the another option is to consider the spherical harmonics. and solve the gravity. And again, this is only applicable to spherical symmetric model. But as we know that the real Earth model are not spherical symmetric. And the third choice is to approximate the gravity on the surface using so-called first principle, for which each point on the surface we need to carry out the volumetric integral through the entire domain, and which is again very costly. And another thing is that the displacement and the gravity has the time lag in here. That's why we need some sort of iterative procedure. And as you already know that this is a very huge problem, if we have to resort to this iterative procedure, then it's very, very costly computation. That's why the problem is it possible to consider full 3D model in an efficient manner? So that is our goal, and we want to solve this problem. And the answer seems to be yes. And we found out that in classical fluid mechanics problem, people were using so-called infinite element method from 1980s. And the idea was very simple. We need to consider the single layer of so-called infinite elements, and the infinite element would have the some special properties than the classical finite element or a spectral element. So let me describe what this infinite element is. So first, let me illustrate the finite element or the spectral element. So in the left, I have the simple one-dimensional finite element, which has 3 nodes, namely x1, x2, and x3. So in finite element or spectral element, we need to do the numerical integration. That's why we need to map this element to natural coordinates, which starts from -1 to +1, as you can see in the bottom figure. And this element has to be mapped by defining the 3 step functions on x1, x2, and x3. For example, m1 is the step function defined over the node x1. So it has the value 1 over that node and 0 elsewhere, and similarly other step function. So this is very simple mapping for the numerical integration. For the infinite element, it's a little tricky and very interesting. So again, I display the 3-noded infinite element on the right. So x3, the node on the edge, lies at the infinity. So now, in order to map this geometry, we do not define this step function like finite element on x1, x2, and x3. Instead, we introduce the so-called pole or some fictitious nodes x0, which is opposite to the infinite direction. And now the step function we defined are only this x0 and intermediate node x2. And this x0 and x2 has to be defined such that when we map this geometry in the natural coordinates, it automatically maps to the infinity. And as you can see, this step function m1 and m2, these are very interesting properties. The summation of these step functions always 1 everywhere. And so as we go to the right, so this both tends to go to infinity, and that is because we want to map that geometrical point to the infinity. So this is the 3D infinite element. It's similar to before, just in the 3D setting. But now the question is why that kind of definition of the step function actually works or represents the decaying function that is suitable for the gravity or any other functions or parameters. So the idea is very simple. So in finite element or spectral element method, so the discretization is nothing but just to represent the variable in terms of polynomial. For example, if p, the gravity, we want to represent that in terms of polynomial of degree 3 or whatever the number of nodes we take. So a0, a1 here are just the coefficients or constants, and whereas the chi square is the variable. So now we define the step function in previous page, and we can substitute the value of x and represents the x minus x0 to be r. And if you substitute this value in that equation, we are ended with this beautiful equation, which clearly shows that when r tends to infinity, this phi decays to b0. In our case, because we want that to be 0, So B0 is 0. So this is very interesting because just what we did is define the mapping or Jacobian the mapping slightly differently than the classical finite element in order to map infinity to the finite region. And the consequence is that the variable just changes to the decaying function according to such that when it tends to infinity, then the value decays to certain constant. In our case, B0 is just 0. So now we have the fairly nice idea what is infinite element, and now take a look at what is the spectral element method, which is widely used in wave propagation and fluid mechanics. So in the left figure, I display the classical finite element, so in which the interpolation points in open circle and the quadrature or integration point in the dark circle are not coincided. So the result is that the mass matrix is never a diagonal. On the other hand, in the right figure, the spectral element method consider the identical interpolation points in integration, and that results in the orthogonality of the interpolation function, resulting in the diagonal mass matrix. So that is the big advantage in the spectral element method, because now for the explicit time scheme, so inversion of mass matrix is just straightforward. You take the reciprocal of each diagonal element. So in short, we can say that the spectral element method combines the flexibility of finite element method with the stability of spectral element method. So now let's see how we can combine this spectral element method with the infinite element method. So for the clarity, I just displayed the 2D typical spectral element, in which again interpolation points and quadrature points are shown and are coincident in order to have the diagonal mass matrix. So now the infinite element on the right has the different quadrature points. So it has the same interpolation points and the spectral element points, but the quadrature points are different. So we cannot use the similar quadrature points as the spectral element, because at the right edge or at the infinity, the Jacobian would be singular if we use the quadrature points that we are using the spectral element. That's why we use the two different quadrature points to combine this spectral and infinite element. So in spectral element, we use the nodal quadrature, or so-called Gauss-Legendre-Lobato quadrature, and on the infinite element we cannot use that quadrature. That's why we use the so-called Radau quadrature. And as you can see that the spectral element and infinite element interface has the identical quadrature and interpolation points, which naturally couples this spectral element and infinite element. So a spectral element is used in the domain, for example, or whatever we are solving, and the infinite element represents the outer space of that domain, for example, for the gravity outside the Earth. So this is how we couple a spectral element and infinite element. So now let's take a look at some example. So we need a special kind of meshing, but it's not that different from the classical meshing that we're using in the spectral theory Cartesian or spectral theory globe. So the only difference is that now we need to add the extra layer of so-called infinite element layer. And this infinite element has to be defined such that the lateral edge of this element never converges at the infinity. And that is the case because, as you can see, that this is radially diverging. So its infinite element will also have the diverging lateral edges, so it will never converges at the infinity. So that's the only requirement that we need to have for the infinite element. So this is the one chunk of the mesh, and the central square is the inner core, and this blue region is the outer core, and then this is the cross mantle, and on the top we have the infinite element layer. So the first example is, of course, the computation of the background gravity on the Earth model. So in the left you can see the gravity field in the one chunk, and on the right plotted the radial profile of the gravity compared with the semi-analytical method. And as you can see that this gravity is largest in the core mantle boundary, and the result perfectly match with the semi-analytical technique, verifying that this infinite element technique works very well. And the computational cost as compared to the classical method is not significantly increased, because we need to add only the single layer of elements surrounding the original domain. So now the second example is very simple. This is the simple response under the so-called IGE ice model. So I have computed here just first few iterations, the displacement field. So at that time there was a big ice sheet above the Canada, but due to the global warming and this glacial rebound, there is no more ice there. So now we can compute this kind of thing very easily with this new package. And the idea is ultimately use this forward simulation and assimilate this with the real data and try to constrain the viscoelastic model or internal structure of the Earth. And then this is the simple example under the tidal loading. So this is the particular instant on the Earth. This response is due to the moon, gravitational potential of the moon. The red zone represents the higher tide, and blue zone represents the lower tide. So with this package, we would be able to compute this kind of tidal response, or response caused by, let's say, black hole or any terrestrial object on the Earth, or even any planets. So now the third example is post-earthquake relaxation, and this is the Nepal earthquake, which occurred on April 25, 2015. And incidentally, I was there during that earthquake, and we lost about 8,000 lives, and more than 20,000 people are injured. So anyway, I just wanted to compute the post-earthquake relaxation due to this earthquake. And the idea is that with this precise and versatile calculation, we will be able to better predict the after pattern or the stress field distribution due to the earthquake, which would affect the triggering of the other faults or bursting. So we are just in the initial stage, and I will show you the displacement component. And the first is the north component, and second is the east, and the last one is the vertical component. And the interesting thing here in the first figure is that this displacement field north component represents the more or less the actual faulting mechanism at that area. So the red represents the northward displacement, whereas the blue represents the southward displacement. And this is exactly the scenario in the Nepal. So where the Indian plate, which is in the red zone, it's subducting beneath the Tibetan plate, which is in the blue zone. So our goal here is to include other realistic major fault structure there, and do this kind of forward simulation in to study this aftershock pattern, as well as the possible future triggering, and also estimate the real data from there to possibly constrain the internal structure of the Earth in that area. So similarly, we computed the post-earthquake relaxation response also for the Bolivia earthquake, which was occurred in 1994 June 9. And here again, we have the very nice displacement component field, and if we have the real GPS data or something, it would be great. We can then compare this to this kind of numerical simulation, and hopefully try to constrain the viscoelastic structure or the internal structure of the Earth. So finally, I will show you another example, which is in the frequency domain. So now our package is set for both explicit time skin and implicit time skin, as well as the frequency domain. For low frequency signal or for loud earthquake, if we want to use the explicit time scheme, then firstly it is not accurate, and second, it would take the several months or several days, and that is not feasible. And that's why we wanted to use the frequency domain approach, and it seems to be very difficult and challenging, but at the same time very interesting. So as you know that the earth it's kind of the musical instrument, so it rings like a bell for several days after the big earthquakes. So with this frequency domain approach, we would be able to compute this kind of the modes of the earth. So here, what I'm showing in this page is just these fundamental modes of the earth during that earthquake. So these modes do not depend on how large the earthquake or where the earthquake was located. They only depend on the material properties and the geometry of the earth. But that the earthquake, the given earthquake, will only dictate that by how much which mode will be excited. And so with this frequency domain approach, we are able to directly compute this kind of spectral response. So in the first figure, we have the 0s2 mode, and in the second figure, we have the 0s3 mode, degree 3 mode, and similarly 0s4 and 0s5 mode. And in mathematical sense, it really amazes me in the fact that we have the diagonal mass matrix, and with the changing frequency, we'll have fraction of changes on the diagonal of the matrix. And with that fraction change, we get this kind of drastic response, and which is in mathematical term, it's pretty remarkable to me. And so here I show you the movie of the 0s2 mode and 0s3 mode. So as you can see that initially just quiet, but when it hits the certain eigenfrequency, then it suddenly boom, and we can see this the modes popping up through the Earth surface. So I will play this movie again. The first is the 0s2 and the second is the 0s3. Yeah. So the idea of this frequency domain approach is that today we are not able to harness the data from the very large earthquakes due to the lack of numerical tools to reliably compute the synthetic data. But with this frequency domain approach, we would be able to compute this kind of synthetic data also for the large earthquakes. And so we hope to harness those huge amount of data from these large earthquakes. So finally, I just want to conclude my talk. So now we are able to obtain the solution of complete governing equations. So that allows us to solve several problems in global geodynamics. For example, earthquake wave propagation in short period and for the long period band, it doesn't matter because we have both explicit time scheme and implicit time scheme, and also time domain and frequency domain, and that is a nice thing. And also we can solve the glacial isostatic adjustment, and ultimately we can be able to compute the sea level changes, and our own graduate students is working on that. And we can also compute this kind of normal modes for the earthquake numerically, and that is a very interesting thing. And then we can also compute this tidal flooding response for this earth, this thing, and also we can simulate the post-earthquake relaxation considering the appropriate rheology. And the interesting thing is that we are able to do these all things in the full 3D model. Thank you. So if you have any questions, I can take questions.
So there's some questions being typed into the chat window right now. I don't know if you can see them.
Yeah.
So first question was, What effect this method has on computation time, say relative to a regular SEM computation?
Yeah, so that is a very interesting question. So, well, if we just want to make one-by-one comparison, so then the computational cost with regard to infinite element approach is not significantly larger because we add just a single layer of elements surrounding the domain. But for the implicit scheme, for both classical finite element or the spectral element technique, infinite element technique, the timing would be significantly larger. But that is not due to the infinite element, but due to the fact that the problem itself is huge.
There are some other questions coming
in. Another, did I answer that question?
A couple of other questions being typed.
Yeah, so actually I prepared this shorter select.
Hold on a second while those come in.
Yes, please go ahead.
Maybe see it. So the next question was, is the non-diagonalization of the mass matrix does not significantly impact the computation time relative to the normal SEM computation? So that's a follow-up to the past question.
Yeah. Oh, so what is the question?
Did you hear that?
No.
Oh, so the question.
Can you repeat the question again, please?
Yeah. So the question. This was a follow-up question from Alex. He asks, does the non-diagonalization of the mass matrix, does it not significantly impact computation time relative to the normal SEM computation?
Oh, so in this in our spectral element, infinite element method, there is no non-diagonalization. So the mass matrix is diagonalized. It's diagonal by nature due to the quadrature that we use. The interesting thing to observe here is that the infinite element region is in the outer space, so there is no displacement, and that's why there is no mass matrix. So that part is essentially zero in the mass matrix.
So Amir is asking, says, thank you for the lecture, and wonders whether you neglect the perturbation of gravity. How tricky is it going to be in your idea? What makes it more tricky in that case? In other words, the perturbation of gravity.
If we neglect the gravity, then it will be pretty easy because the infinite element is necessary only to solve that gravity. But for the long period response, let's say more than larger than 200 seconds, this can be very significant, and especially for this long-term response like glacial rebound and those things, and this is very significant, and we cannot neglect the gravity perturbation.
The next question is, how does a single layer of elements handle the singularity of the center of the Earth?
With singularity.
With
singularity. So the idea here is that the thing is yeah. So the idea is that the when we solve the Poisson's equation, so we have the classical spectral element in entire Earth model, but then we just add the single infinite element layer outside the domain. So there is no singularity involved in the numerical approach here. So only singularity that we encounter is that if we use the same nodal quadrature as the spectral element in infinite element, and that will be the singularity in the edge, but that we are able to avoid using the different kind of quadrature.
Does that answer the question? Yes. Alex is going to ask a follow-up question. Oh, okay, I'm going to unmute the microphone.
Mm-hmm.
There you go. I'm unmuting Alex's microphone, I think.
Hello? Can you hear me?
Okay, your mic should be.
Okay, so good talk.
Hello?
Looks really.
Yes, I can hear you.
Looks really interesting. Thanks, Jeroen. Hi. You can hear me? Looks really interesting. Okay. Okay. Sorry.
Yeah.
Hi. I was wondering how accurately you compute the gravity. Okay. Sorry. I was wondering.
I think it's for example, for this background gravity, which almost perfect match, and also we compared our wave propagation with the normal mode approach.
Okay.
And we almost got identical results, so it should be very accurate. Yeah. You're welcome.
Are there any additional questions?
Yeah. Any other questions?
If no one else has one, I have another one.
While we're waiting for people
I was wondering
if their questions.
Yeah, of course, please.
I will just do a couple.
I was wondering if.
Oh, go ahead. Go ahead.
I was wondering if you're planning on releasing the code, and if so, when?
Well, while we're waiting for people to see if they haven't think about what they're thinking.
Yes, definitely, yes. So, our original plan was to release this software before today's webinar, but as you imagine that it's very huge package, and it's entirely different package than the SpecFM 3D, and that's why it's currently under very intensive benchmarking and testing. So we plan to release it very soon, although I don't have the definitive date. But it's already available as the development version in the GitHub. Not the GitHub, sorry. It's in the Bitbucket right now. We can give the access. But publicly, I think we are trying very hard.
If I potentially could get access to the version you have right now, I'd email you, and that would be good. Okay, thank you very much. The version you have right now.
Yeah, definitely. Yeah. So we have the different structural organization for this package. So we need a slightly different the user experience, but it's very similar to existing SpecFM 3D, Cartesian, and Globe. Yep.
Okay, so we are getting close to the time. So I'm going to make a couple of reminders and announcements for the future, and people can think about whether they have a last question or two. As always, more information on this and all events ICAG can be found on our website at geodynamics.org, and that includes the recordings of all past webinars. And I want to thank everyone who participated in today's webinar, and especially our speaker, for giving such an interesting and valuable presentation. Our next our next webinar will be April 6th, and that will be Brad Agard, and he'll be talking about an overview of PILA, plus a preview of multiphysics and other features coming in PILA 3.0. So if there are no other additional questions, I'd like to thank our speaker again, and thank everybody for participating, and that concludes our webinar.